Now let's see the concept of finding areas with respect to y-axis. All the problems which are considered were along x-axis or over dx. So the next concept is finding areas with respect to y-axis. That is, say for example, I have x-axis and y-axis in my origin, which gives two curves. Say for example, I have the curve y equals f of x and y equals g of x. So for these two curves, let me say the two bounds are y equals b and y equals a, through which I am going to find Now I want to find area of this shaded region, but the only difference between the previous problem and this problem is that in the previous case the limits were considered with respect to x-axis, but here the limits are considered with respect to y-axis, perpendicular to y-axis. Therefore, this is about finding areas with respect to y-axis. How do we find area of this region which is with respect to y-axis is the biggest question here. So as I see this x-axis and y-axis, I see that my lower limit is y equal to a, because this is the least from here. The distance here is a and this whole will be b, so a is less than b. So clearly I find that a is less than b. But because it is about finding the areas with respect to y-axis, the whole of x changes to y. With respect to y-axis is about dx, with respect to y-axis is about dy. And therefore, area of the required region is given by integral x changes to y. The lower limit of y is a and the upper limit of this is b. And when I have y equals f of x, implies x is f inverse y, and y equals g of x implies x is g inverse y. Okay, so in this case we find the areas using upper curve. The upper curve in this case is this and the lower curve is this, because when you see with respect to y-axis, this acts as the upper curve and this acts below y-axis, nearer and further. So therefore my upper curve is given by y equal to f of x, so x is f inverse y, so I get this as f inverse y minus g inverse y of dy. So the whole of this is transformed into of f inverse y minus g inverse y of dy is what we get in terms of y. So the difference we find between the previous case and this case is that here we have all y's and there they were all x, because this is with respect to y-axis and that was with respect to x-axis. So area of this shaded region with respect to y-axis is integral lower limit a to upper limit b of upper curve, which is this, and the lower curve which is given by this dy, is how we get this. So as we have seen the special cases with respect to x-axis, similarly let's see some special cases of finding areas with respect to y-axis. So in this case, suppose my curve is y equal to f of x, or x equals f inverse y, because when y is f of x, x will be this. Then in order to find area of the shaded region, and this is the upper limit, which is y equal to b, and finding area of this shaded region comes as the special case of only one curve. So in case of the special case, I have the area which is found using integral y equals a to b of upper curve, which is f inverse y, and lower curve is y-axis, but y-axis has the equation x equal to 0. So this acts as the lower curve as the y-axis itself. So equation of y-axis being x equal to 0, I get the lower curve, which is this of dy. So this reduces to f inverse y dy. So area under the curve is given by integral a to b, y equals a to b, f inverse y dy, if the area is in this form. Next, let's see the next case of where x-axis and y-axis and origin. So in this case, let's see what happens if the curve is somewhere here. That is, if I have this curve y equals f of x with the bounds y equals a and y equals b, then in this case I get my shaded region on the second quadrant, that is in the negative side of x. Okay. So in this case, to find the area, we have area is integral of lower limit to upper limit of the upper curve here is x equal to 0. So y-axis acts as the upper curve. So upper curve is 0 because it is on the top. As you see along y-axis, this is the upper curve and this is the lower curve, because this is with respect to y-axis. So upper curve minus the lower curve of dx. That implies a is integral a to b of minus f inverse y dy. Is how we get the area as negative sign, because the curve is in the left side of y-axis, the negative side of x-axis. Now next we have the case where the curve has y-intercepts, that is, the curve cuts at the y-intercepts b and a. So in this case of the curve, which is y equals f of x or x equals f inverse y, then let's see what is the area of this shaded region. Now in this case we see that there are no lower and upper bounds, but the intercepts will decide the lower and upper limits. As you draw a line passing through A, I clearly see that the line passing through B and parallel to x-axis is y equal to B, and the line passing through A is y equal to A, is how we get the limits using the x-intercepts. So once we get the limits, then the required area is integral lower limit to the upper limit of the upper curve minus lower curve dy, which we obtain as integral y equals a to b f inverse y dy. Finding the areas using x-intercepts converted into the limits gives the formula integral this for this area. Now suppose I have a case where this is y-axis and this is x-axis, and I have y equals b, and suppose this is y equals a, then what if I find the equation of this curve, which is something like this? I want to find area of this region and area of this region. So in order to find areas of these kind of problems where you need to find area of this shaded region, then I just split this into y equals to a, and the equation of x-axis is y equal to 0. So I split between 0 and b and 0 and a, then I add the two areas. So initially if I take this as a1 and this as a2, I clearly see that my a1 is obtained by taking for a1, if you see with respect to y-axis, the lower limit is 0 and the upper limit is b. So 0 to b of upper curve minus lower curve, the upper curve is f inverse y and the lower curve is 0, so I get this to be f inverse y dy. Similarly, when I take my a2, my area a2 is the lower limit, which is a, and the upper limit, which is 0, because when you're starting from down, this is the lower limit and this is the upper limit. So for this, I have y equals a to 0 of the upper curve. The upper curve is x equal to 0 because here y-axis is the upper curve. So upper curve minus lower curve dy. And therefore we add a1 and a2, then we get the required area. So as we see this, therefore a is this plus this, that is integral 0 to b f inverse y dy minus integral a to 0 of f inverse y dy is what we get when you add two areas a1 and a2, giving us this. So sometimes we need to add the two areas which are split using the limits accordingly for both the areas. Next, let's see the next special case where I have my x-axis and my y-axis where I have two intersecting curves like this. So when I have two curves in this form, then one of the curve, let me assume as y equals f of x, y equals g of x. So as I see these two curves, we find the points of intersections, but we don't have the limits. Therefore, the limits are nothing but the y coordinates of the point of intersection. So therefore, if I take the point of intersection here as A and here as B, then area of this shaded region is found using the points of intersections. So lower limit is the y coordinate of B, that is the point of intersection of the two curves, and upper limit is y coordinate of A, is what we get. Therefore, the required area would be integral of, if I assume this lower limit, the y coordinate of the point of intersection as y equal to A and this is y equal to B, then I get this y equals A to B of upper curve is what we get as the area using integrals. So finding the areas of these special case where there are no limits given, but we use the points of intersections to derive the limits is given in this form. Now let's see some related problems connected with finding areas, both with respect to x-axis and with respect to y-axis. As we have seen with all the various types of cases of finding areas, both with respect to x and y axis, now let's see some example problems to understand the concept more better. Say for example, I have a question which says, find the area enclosed by y equal to 3x and y equals x squared. Now, the questions which are given in this session are related to finding areas, but we don't have the exact diagrams given xy coordinate system. Therefore, the given curves we try to sketch on the xy coordinate system, and hence graphing concept is more important in doing these kind of problems. If we want to understand these problems more better, we should understand the sketching of the curves concept more better. A continuous practice on sketching the curves exactly through x and y intercepts and exact shape is how we need to practice. Therefore, understanding the knowledge of finding or sketching the curves is more important in finding the areas under the curves. So therefore, in order to find the area enclosed by these two curves, I clearly see that the curve y equal to 3x is a straight line. The knowledge of a straight line which we have learnt in the lower classes makes us understand that this is a straight line passing through origin. So this is curve 1, and then the next curve which is given out here is this, which I can write as this. Now clearly I see that this is a quadratic equation or a quadratic curve, therefore this is a parabola. So this is a straight line and this is a parabola. Now we combine the straight line and parabola in the xy coordinate system, understand its x-intercepts and y-intercepts and the points of intersections. Then with the exact shape which we get through xy coordinate system, we decide on which curve is above and which curve is below, because we need to know the bounds and the upper and the lower curve in order to find the areas. So we try to sketch these two curves on an xy coordinate system and identify the lower and upper bound, or the lower and the upper limit, and also we identify the curve which is upper and the curve which is lower. So let's see how we can do that. So let's see how we can sketch the two curves y equals 3x and y equals 6x minus x squared, or 6 minus x. So let's see how we can sketch these two curves on the xy coordinate system. Clearly, y is equal to 3x is the line passing through origin, is how it looks. So this is the curve y equals 3x, and y equals the quadratic, which is x into x, 6 minus x, implies its x-intercepts are obtained when I take y equal to 0. So this graph cuts x-axis at 0 and 6. So the parabola cuts x-axis at 0 and 6, and because the coefficient of x squared is negative, the parabola is inverted because a is less than 0, all we have learnt in quadratic equations. So therefore this is an inverted parabola which comes like this. Now therefore the parabola is like this. It cuts somewhere here, and therefore the inverted parabola and the straight line, as we see here, are just making some region, that is, the line and the curve make this region which is bounded between 2 points. So it is now our task to find area of this region using the left bound, which is x equal to 0, and the right bound, which is obtained here. But in order to find the right bound, I need to find the point of intersection, which I'm going to find using the line and the curve. So let's find the point of intersection, because this point of intersection is already known as origin, and this point of intersection we need to find by solving the curve and the line. So to find point of intersection, I take 3x, which is x times 6 minus x, because in order to solve the point of intersection, we equate the line and the parabola, and hence I get this to be 6x minus x squared minus 3x equal to 0, and 3x minus x squared equal to 0. So one of the x coordinate is x equal to 0, and the other x coordinate of this point of intersection is x equal to 3. So we don't require the y coordinate, therefore we just find this right bound, which is x equal to 3. So the left limit is x equal to 0 and the right limit is x equal to 3. And clearly when I see the diagram, as I see here, this parabola is upper curve and the straight line is the lower curve. So therefore the required area of the shaded region is integral lower limit of x with respect to x-axis and upper limit of x of upper curve. As I see the upper curve is parabola, and line is below the curve, so the line is the lower curve. So my upper curve is 6x minus x squared minus lower curve, which is 3x of dx. That is integral 0 to 3, 6x minus 3x is 3x minus x squared of dx is what we get. Then integrating this, integral 3x is 3x squared by 2 minus x cubed by 3 with limits from 0 to 3. Now, using the limits, upper limit is 3 times of 3 squared by 2 minus 3 cubed by 3, and then the lower limit which is substituted, which gives us the required area. So continue from there. I find the required area to be 3 times of 3 squared by 2 minus 3 cubed by 3 minus 0, 3 times of 0 squared by 2 minus 0 cubed by 3 is how we get with upper limit substituted minus lower limit substituted in the function. That implies a is 3 times of 3 squared, that is 3 cubed by 2 minus 0. Of this. Is how we get when we simplify the answer through cancellation. Therefore, area of the required region is approximately 4.5 square units. This area is 4.5 square units using the definite integrals. So now that we have completed with the topic of definite integrals, the next is about the learning outcome. That is, when we do the definite integrals, what have we learned out of this is the biggest question. We have found that definite integral helps mainly in finding areas of any irregular shapes bounded between the two lines. So definite integral helps in this, and the next learning outcome is that I need to have thorough knowledge of sketching the graphs of given equations. If we do not know how to sketch the graphs, we cannot do the problems related to finding areas, because the whole of areas is related to XY coordinate system. Therefore, need to have thorough knowledge of sketching the graphs. Then the next learning outcome is I understand the difference between integration and definite integration. I understand that integration has an integral constant c. That means it can accept any c. So different answers are obtained for the integration which we solve. But definite integration is a fixed constant, does not change. This changes with c. This does not change with c. is how we come with the learning outcome in the topic of definite integral. Definite integration is part of integration which helps us in finding the areas bounded between two lines.